if every element of a group has torsion, and more particularly if we have a square equals to identity for all A in the group. So you act it once by A and then it gets back to identity. So A, when hit by A, it goes to identity. If that happens for every element of the group, then we can say something very interesting about the group, and that is then G must be abelian. See, the group theoretic proof of this fact is actually not very difficult. It's quite simple. But this intuition is much more valuable in the long run. When you are dealing with more complicated groups, this intuition of torsion is more valuable, because oftentimes you actually draw a picture of a group, in more precise sense the Cayley graph of a group, and then this bouncing around thing has more precise meaning. So keep this intuition in mind. So we have so how can we prove this? How can we prove that G is abelian? All right, so if we want to, abelian means it's commutative, so we want to show that AB is equal to BA for all A and B. So what we do is we use the fact that every element is identity. If we square every element, we get identity. So AB, if we square it, has to be identity. But that is also equal to A square times B square, right? Because A square is identity, B square is identity. Because every element is identity, right? So what do we have? We have AB is equals to A square is AA, BB. And we are done, because we can multiply to the left by A inverse and multiply to the right by B inverse. And we get AB, I'm sorry, this one becomes BA, and this one is AB. So BA becomes equal to AB. It's a simple group theoretic proof, but the implication is quite exceptional. In the next follow-up lecture, we will talk about a very interesting group, which is sometimes called the symmetric difference group in the domain of set of sets, and how this particular property immediately reveals that that particular group is an abelian group. So that will be an application of this property. Thank you for watching.